Whether you are asking a chatbot to write a poem, generating digital art, or letting an autonomous system drive your car, you are interacting with artificial intelligence. And if you peel back the layers of those famous models, like ChatGPT or Tesla's autopilot, you will find the exact same mathematical engine running quietly in the background. That engine is PyTorch. It is an open-source machine learning framework. Think of it as a specialized toolkit that allows you to design and build complex neural networks using standard everyday Python code. Building a modern neural network requires coordinating millions of simultaneous mathematical operations. If a developer had to manually write the code to track every single one of those calculations from scratch, a single model would be almost impossible to manage. PyTorch acts as a universal translation layer. It takes all of that abstract, mind-bending calculus and linear algebra and packages it into a clean, accessible digital workspace. It allows anyone with basic programming knowledge to direct massive amounts of computing power. Back in the early 2010s, inside university labs, deep learning was starting to show incredible promise. But the tools to build these systems were notoriously difficult to use. Researchers were spending weeks fighting with their own code, writing hundreds of lines just to set up basic math, rather than actually testing new ideas. Early frameworks relied on what is called a static computation graph. Think of this like plumbing. You had to fully build and weld together a rigid pipeline of mathematical operations before any data was allowed to flow through it. If you made a mistake, or if a differently shaped piece of data arrived, the pipeline snapped. You had to stop everything and rebuild it from scratch. But PyTorch offered a different path, the dynamic computation graph. Instead of building the entire rigid pipe system up front, the pathway is built and modified in real time as your code runs. The network adapts on the fly to fit the data passing through it. The engineering team at Meta AI accomplished this by taking an older, highly efficient math library called Torch and wrapping it in Python, the most popular, easy-to-read programming language in the scientific community. By prioritizing a fluid, readable coding experience over rigid, pre-planned structures, developers could suddenly test new ideas in minutes instead of days. This accessibility is the primary reason PyTorch became the standard tool in AI research. To understand how you actually build something with PyTorch, we have to look at its core building block, the tensor. Conceptually, a tensor is just a container for numbers. It can be a single dot. It can stretch into a line, expand into a grid, and stack outward to become a massive three-dimensional cube of data. These mathematical cubes map directly to the real world. A color image, for example, is just a three-dimensional tensor. It has height, width, and 3 color layers. Every pixel is simply a number inside that tensor. Real neural networks process thousands of these images at once. Pushing that much data through math formulas requires pushing the calculation off your computer's standard processor, the CPU, and onto specialized hardware. A CPU is like a single executive. It is very smart, but it can only handle a few complex tasks at a time. A GPU, or graphics processing unit, is like an army of thousands of workers calculating simultaneously. They are built specifically to do simple math on massive grids of numbers all at once. PyTorch is designed to take these tensor structures and push them into that army of GPU workers instantly. With one line of code, you can move millions of data points onto specialized hardware, making your math much faster. So you have your data and your hardware ready. But for the model to improve, it needs a way to realize it made a mistake and then actually fix it. The engine that handles this is called autograd. It acts as a silent bookkeeper, quietly tracking every single mathematical operation that occurs as your data flows through the model. When you feed data into your model, it travels through a web of connected layers in what is called the forward pass. The model makes a final guess. If that guess is wrong, the system measures exactly how large the error is. Because autograd kept a perfect record of the journey, it triggers a backward pass. It calculates the exact mathematical tweaks needed to fix the error, and it sends a signal surging backward through the entire network, telling every single connection exactly how it needs to change. Finally, an algorithm called an optimizer takes those tweaks and turns the dials of the model. It updates the strength of every connection so that the next time that same data passes through, the final guess is a little more accurate. Without this engine, developers would spend years doing calculus by hand to figure out how to adjust their models. By tracking the math and calculating the required adjustments automatically, autograd handles the logic of learning for you. That cycle is how nearly every modern AI model is built. You pack data into tensors, blast them through GPUs for speed, and use autograd to evaluate mistakes and adjust the strength of your connections. Even though there is massive complexity in the background, you primarily interact with clean, readable Python code. PyTorch handles the heavy lifting, so you can focus on the design. Now that you understand how the system works, it is time to start building. In our next session, we are going to dive directly into tensors, learning how to create them, shape them, and manipulate the data inside. You are learning the same toolkit that researchers use to develop protein folding models and the language systems we use every day. By making the math of learning accessible, PyTorch has become the primary workbench for the entire field of AI research. I will see you in the next one.